Okay, let's continue then. We were talking about, on the last lecture, user interface design. We're going to wrap that up this morning with a few details. And then we're going to start into Chapter 8. So on the slides preceding slide 33, we've been talking about guidelines for user interface design and what constitutes good and bad things. Principally, we listed a bunch of things that you should do, such as be consistent and a variety of things. Consider the needs of different groups of users, etc. On slide 33, I'm listing a bunch of coding techniques or encoding techniques. We have one of the principles where we said you should make sure that when you're doing design that you choose good encoding techniques for information. And I already talked about some of these orally. So this is sort of a review. These are some of the ways that you can express information in your designs. Okay, so everybody knows about using text, and that's the sort of standard, the most historical way. We've also got buttons and other kinds of widgets and things like that. But you can use icons, photographs, diagrams. You can use color coding for various kinds of information. Grouping and bordering, very powerful techniques to group things together, put boxes around them, or maybe you don't even put boxes around them, maybe you just group things, leave some space and group some more things. And the very fact that you've left that space tells the person who's looking, there's something different about the stuff that was grouped above and the stuff that's grouped below. Spoken words, okay, that's speech, music, can be used to encode information. It's certainly used in entertainment systems to encode the mood. Certainly little sounds that indicate certain things have happened. Other sounds that are more abstract in nature, like beeps and clicks and things. Animations and video is putting a lot of this stuff together, I guess. And flashing. Flashing I put last. It's generally speaking considered bad. Okay, so don't code information using flashing things. For a number of reasons. One is that it tends to annoy people more than anything else, unless you really want to draw their attention to an emergency. Like flashing lights can be used to, as fire alarms, for example, so that blind people, so that deaf people can tell that there is, in fact, a fire. Okay, and in fact, that's what happens. You see flashing lights as well as loud sounds these days. But flashing, if done wrong, can also lead to epileptic seizures and things like that. So you need to be cautious about that. In the book, there is a page where I've listed these encoding techniques, and I've given their advantages and disadvantages. And that's a quick summary you should look at. Obviously, you could take a whole course in this kind of stuff. I'm going to take a quick look at an example user interface, a very trivial user interface that has a number of things that are just plain bad, and that have been fixed to some extent. Okay, just to illustrate the kinds of things that people do without thinking about it, and then a few very quick and easy changes you can make, which will improve some UIs. Okay, so this is a 4-panel system for entering some information, signing up for some kind of credit, I guess, some kind of credit card or something like that. It doesn't even say. It says Utamlia sign up, totally uninformative. To start with, the system should tell you a little bit more about them. On the after page, which is slide 35, it's a little bit. It says Welcome to Utamlia Services. Probably should still say what this does. Okay, it says to sign up, click on Start, but the bad case just has a menu, and it says to sign up, use the edit menu. Well, I mean, why force people to use a menu when you have plenty of space available on the screen to have an icon to do it? Right. Okay, so that's one of the problems with this first panel. On the second panel, in the bad case, it says name, number, expiration date, and the title is payment with cancel and OK button. Okay, the improved version, okay, has, in fact, we probably ought to look at the 2 panels. We probably ought to look at the second panel and the third one, which is the bottom left panel, where in the bad example it's got things like name, your email, okay, cancel, and then a whole bunch of fields to fill in: street, municipality, county, postal code, phone, type, etc. Okay. Now, on the improved version, what we've done is we've said, okay, the person has to type their name, existing email, and then we've used the tab dialog to allow people to capture perhaps more than one address, home and work mailing address, because some people, when they're forced to type one address, they don't know whether they're supposed to type their home address or their work address, or maybe they want all of them. So this gives a little bit more flexibility for this kind of information. It gives you the flexibility to have different kinds of addresses available. We've also changed the buttons at the bottom. Instead of saying OK and cancel, they say previous and next. And this then gives the user the ability to go back to the first stage. Okay, I can go back at the beginning, I can see what it's all about, and the next as I can go on, and that previous and next continues on the next panel down below. Okay, now this is all about signing up for a credit card, or signing up for some product, I guess, where you're paying with a credit card. And in fact, in the old example, the panel number 2, number, is just supposed to be credit card number or an expiration date. What we're doing here is we're changing it so that they can, explicitly say what kind of card, and in fact it should probably still say credit card number, but now at least we know it's a credit card because it's indicated. And there's a space for the expiration date and in a nice little box. Okay, so we've boxed some of these things as well to show this is the payment information. And down below we've said total monthly fee $20, whereas in the previous example it just said amount $20. Okay, so it's giving us more information. It's saying the monthly fee. And then there's a little statement in the good example saying my credit card will be debited the first day of each month for the above amount. Okay, so that's telling people what happens when they acknowledge this. The buttons at the bottom, instead of just saying OK and cancel, are giving them previous, which means go back and allow you to edit changes to things, maybe edit your existing email, your name, or whatever. Cancel, which is self-explanatory, and I agree. Okay, so rather than just saying OK, it's saying I agree, which gives the user more of a pause. Okay, I'm agreeing to something. What am I agreeing to? I better read it, right? I'm not just saying OK. Otherwise the user might tend to just click OK, thinking, well, I haven't paid yet. But this I agree is committing them to this debit, and so you really want to be clear about telling people what they're doing when they click on buttons. There's also help buttons, by the way, and little question marks in the good example, which weren't present before. And there are some, it says step 1, step 2, step 3. It says step 5 here. I'm assuming that there's some steps missing from this information, such as what I'm planning to buy and stuff like that. I mean, the panel's missing from both the good and the bad example. And finally, on the final page, there's information. The system is now dialing in to register for our services. Presumably, if we knew what the services were, we should say exactly what they were. Please stand by. There's a cancel button allowing me to cancel at some point. On the previous one, it just said signing you up, cancel. Okay, so there's a bit more information here. It tells you the progress, how much time it expects to be remaining, etc. Okay, so basically we've made some improvements. There could be more improvements made to this. If you had a full task analysis and you knew exactly what the products were and so on, you might be able to make a lot more improvements yet again. But you can make some very simple improvements to user interfaces with relatively little work. Any questions about this? And can anybody notice any other improvements that could be made here? Yeah.
You're saying MasterCard or Visa or Amex, aren't you limiting the options for credit cards?
Yeah, in this case, that is being limited. That's a business decision. Okay, so companies might choose to only accept 3 kinds of credit cards and not others. Those clearly are the main ones, but you're right. I mean, but that is a business decision. Hopefully, if you design the underlying system, you would design it to be flexible so that new credit cards could be added as a business decision without changing the code a lot. That would be a good thing to do. Anybody else see any other improvements that could be made, or any thoughts about this? Improvements to the new one. No. I've already mentioned a few things. It could be more informative about what the services are and so on. One of the things is that home, work, and mailing address. What if they're all the same? You know, on the work and mailing tab, it might be good just to say same as home or something like that, or automatically copy the information, something like that, so that people wouldn't have to type the thing again if it was the same. And it might also say optional, optional work address, optional mailing address to inform the user if they weren't required to fill it out. In fact, quite often information is optional, and you should make as much information optional as you can. Right? There might also be some place in here where somebody could say, please do not send me junk mail. I mean, after all, you're giving them the existing email address, right? And so you might want to make sure that there's some kind of acknowledgement of that, but maybe by default, please do not send me junk mail, and you can uncheck that to say, please send me junk mail, That's something that the business rules might not like, but anyway, we'll see. So there are lots of things you could do. So you could work on this a lot more. With one iteration, you made some improvements. You can work on it over and over again to improve it still further. And talking about improving interfaces, evaluating interfaces is a very important thing. Later on, we're going to be talking about testing of software. And that part of the testing is testing the algorithms, testing the input and output, making sure that the output corresponds to the computations we expected as a result of the input. We'll talk about that in some detail in a few lectures' time. But this is another kind of testing. This is testing the user interface with respect to the users and what they want, what they find effective, what difficulties they have. Okay, so it's a very important process, quite different in many respects from the regular testing that you do of your code. Okay, you have to do this with the users or with usability experts present, but preferably with users, and certainly some of it has to be done with users. There are several strategies. One strategy is called heuristic evaluation. This is the strategy where you do use people who are well attuned to what is good and bad about user interfaces. In other words, user interface experts or people software engineers who've been well trained and are well versed in UI design. And a general strategy is to pick some use cases to evaluate, and then you're going to say, okay, we're going to study the parts of the system that rotate around these use cases. For each piece of the system, as you're working through the use case, okay, each window, dialog, page, etc., menu, whatever it might be, you're going to study it in detail and see if any improvements could be made. Okay, so you're going to look back over those guidelines that we had for good user interface design, and plus all of the knowledge that you have as to appropriate use of coding techniques, appropriate flow from step to step, what the user knows, what the user doesn't know, what the user's expectations are, and things like that, and find usability defects to fix. Okay, so basically it's a checklist-based approach where you say, we'll study everything in detail and see if we can possibly make any improvements to it. And you then record every defect you find. It's just like finding bugs in code. You write down the bug and assign somebody to fix it. Well, that's exactly what you do here as well. Okay? So you're not executing the code, you're examining it, because executing it will work, right? It may well work, but it might be unusable. So it has to be the human eye rather than the system executing that tests whether in fact the user interface is good or not. The second technique is evaluating by observation of users, and this is where you absolutely have to have real end users. A collection of end users corresponding to each of the most important actors. So if you have different kinds of actors using your system, you pick a variety of different actors. Again, you focus on a few use cases, because at any given point in time, you can't test the entire system. You might have a goal of doing usability testing on the entire system, but at any given session, any given day, you have to have a focus. Otherwise, you're going to drift off and randomly go over different parts of the system. So whether you're doing heuristic evaluation or observational evaluation, you've got to, at any given point in time, focus on a subsystem or a part that will be today's focus. You're going to write down some instructions for some scenarios. You're going to say, okay, to the users, start off with this data, this information, and try and achieve a certain goal. Okay? And then the users are going to go in and try and achieve a certain goal. Some of the users will be beginners, and they're going to be trying to learn the system as they're trying to achieve the goal. Others might be expert users, and your objective there is to see, can they use the system fast or not? Okay? You're going to arrange an evaluation session with these users, explain the purpose of the evaluation. One of the things you have to do when you're working with users is you have to pay a lot of attention to making sure that the users are comfortable, that they understand what's going on, that you're not testing them. There's some ethical issues involved, because sometimes in a large organization you bring in some users and you say, okay, you're going to use this system, and they might think, well, this is a test for my employment, you know, am I going to get fired if I do a bad job using this system? You know, I might really screw up badly, and the people are going to be scared, thinking, gee, you know, I better not screw up with this system, because otherwise it'll look bad, my boss will see. So there has to be a clear indication to the users that you're expected to do badly. We're testing a system that's got problems in it, and we're just trying to find problems with the system. And it's good if you have difficulties, because other users will have difficulties too. Okay, so these are some of the ethical issues that you have to pay attention to. It's desirable to videotape the sessions, because then you can go back and examine the tapes over and over again. But again, for ethical reasons, you erase the tapes once they're done, because you don't want arbitrary tapes of people surfacing years later and so on. You talk with the users as they're doing the task, so that the users can explain what their thought processes are. And when they're finished, you ask them some questions. It's called debriefing. It's an old military term, where you say, well, what did you like about this? What did you dislike? What problems did you have? What was going through your mind when such and such a thing happened? Okay, and that you'll tease out additional information, still captured on videotape, during the debriefing process. You write down the difficulties, bug reports, but as I say, instead of being algorithmic bugs, they're usability bugs. But they're still bugs, okay? And recommended changes to the system. You say, well, here's the way we think the system should work. And then it gets assigned to some developer to actually make the change. Okay? Any questions then about strategies? This is a very brief overview, but any questions about these strategies for evaluating user interfaces? We're not giving you any practice in doing that in this course. That would be something which you would get practice in a more advanced course. But you should at least know that these are considered engineering best practices, and they should be done in all organizations developing user interfaces. And they're often not done. Remember, I said that usability is one of the weakest links in software engineering as a whole. A lot of people know and pay a lot of attention to technical issues and take great pride in writing programs that work well and are thoroughly tested and don't crash and things like that, but are totally oblivious to the fact that their systems might be unusable. They don't even know it. They don't even realize it. They think that users would understand it because they understand it. But the only reason why they understand it is because they developed it. Okay? Now, other people are very much attuned to other users. So you've got to be able to be empathic is the word. Okay? Empathy is the ability to appreciate what goes on in other people's minds. And so you've got to develop the sense of empathy. You've got to develop a sense of what could go on in people's minds whose minds work quite differently from your own. Okay? It's a general life skill, but it's a skill that's very useful here. Okay? Any more questions or comments? The next few slides talk about implementing a graphical user interface in Java. I'm going to skip over these quite fast because this is something that you really need to sit down with and work through the vast reams of documentation. There are a number of ways of developing user interfaces in Java. There are two toolkits. There's the Abstract Window Toolkit and the Swing Toolkit that are widely used. Swing being the more modern, but Abstract Window Toolkit being a very basic toolkit that's still suitable in some circumstances. There's also some others. There are some other toolkits you can obtain which completely bypass either of these. There's an Eclipse toolkit, which I've done some work in, which was originally developed by IBM here in Ottawa, in fact, and it supports software engineering tools. But they decided they'd create their own graphical toolkit to go along with that. And you can program any application in that. And there are other toolkits available as well. But the most common ones are AWT and Swing, coming directly from Sun. A few pieces of general terminology. We have components. In some sense, another word for widgets or controls. Things like buttons, text fields, lists, labels, scroll bars. These are the classes involved. We have containers, things like frames, dialogues, and panels, which you can put components in for grouping purposes and to make units that can do special things. We know what dialogues are, right? And we have layout managers, things that have to do with controlling aspects of the layout of information on the screen. There's different ways of laying information out. Those are some of the things that you can look at. Again, I leave it up to you to look at the Java doc for these things. This slide 39 shows you just a few of the things that you can do to put together a simple user interface. So this is a user interface which has a large panel at the top, a large text panel, a few smaller panels, host, port, and message with labels and actual boxes, and then some buttons at the bottom. Okay, and in AWT, which is one of the styles, what you do is if you're writing code to do it, you just declare buttons. So new button, you can see them all listed down here. New text field, new labels with various things inside them with certain attributes. So this says right aligned, for example, and a new list. Okay. So there's a number of things that we're putting together here, and as I say, leave it up to you to look at the details, but this is one style. Another style, by the way, involves no programming, involves just drawing pictures on the screen and having the system generate the code. Ultimately, you will get code generated. It'll look something like this. And these days, it's probably desirable to, rather than coding things from scratch, to use these GUI builder tools. Okay, it's more abstract, it's higher level. For the purpose of this course, I'm leaving it up to you to choose the technology. The TAs will give you some guidance in the labs as to the appropriate technology to use. But you can use Swing, you can use AWT, you can do it with GUI building tools, and you can do it with hard coding because you're creating very simple UIs. It might save you some time. But I leave it to you to explore. You've got some weeks to do that. On the next page, we have the constructor of a client graphical user interface for simple chat, which is basically putting, the previous slide was declaring the variables, and this slide we're putting a bunch of things together. So we're adding some of these components to their containers, mostly. That's what's going on here. And then on slide 41, we continue with the code. We have a thing called an action listener. Okay, an action listener is a piece of code that will end up responding to events occurring. Okay, so the key way a lot of these pieces of user interface actually respond to users is that they have methods that you write that get triggered when certain actions occur. So action listeners can listen to button presses and mouse movements and things like that. And so this one, for example, when it gets a certain action performed, it's going to call send. And this is the method send that will actually get invoked. And this is the method where we now end up calling our non-user interface part of the system. So all this code is in the user interface. The other part of the system in a separate class, we said we should separate them. We've got a client class, and we're going to say send a server. Client.send a server. And so that's really the only place where we're actually interacting directly with the client class. So we've got the client UI class and then the client class that we're interacting with when the button gets pressed to send a message. Okay. The code for this is available on the web, and you can take a look at it and digest it, etc. Now, one of the things you're going to be doing, of course, in one of your assignments is, in fact, adding a graphical user interface. And so you'll, between now and then, time to build up some experience with this. But I've just given you a brief introduction. TAs will fill you in further. Any questions? Okay. So the week I'm away, that on the Wednesday, you're going to get some lectures from TAs where they're going to talk about the details of this. Okay, let's wrap up the chapter then by talking about some of the difficulties and risks in the user-oriented issues of software engineering. First major issue is that users differ widely. Okay, users do not think the same. In fact, every individual human being is different from every other individual human being in the way they think, in the knowledge they have, in their attitudes, etc., etc. Okay, so you've got to account for differences differences in preferences, differences in abilities, differences in knowledge, etc. And people differ because they come from different cultures, they speak different languages. Okay, they work in environments with different currencies. All kinds of issues that have to be addressed that come under the heading of internationalization. Okay? Internationalization is a major topic. Whenever you design user interfaces, you should make an assumption. Unless you're absolutely definite it's only going to work in one country. You should make an assumption that this UI might be needed to be used in places where they speak different languages or use different currencies or different date systems or whatever it might be. And in fact, in my graduate course, I spent several lectures on all the many issues to do with internationalization. Okay, and it's not just language and script and currency. There's huge numbers of issues that differ. And being a good UI designer, you need to have awareness raised about that. Medium to large companies generally have people who specialize in these kinds of issues. But all software engineers should have an awareness. Okay? And so when you perform usability studies, the solution to some of these problems is to try and use them with different kinds of users, including, if, for example, if you're here in Canada and you have to develop a system which is English and French, make sure you get French people and English people to use it when they're in the appropriately translated versions. If you're using it on an international scale, get Arabic people and Chinese people and Dutch people and whatever in your target markets to use it, to make sure that the translations are the same. Often technical translators make mistakes. One of the guidelines in internationalization, by the way, is make sure your technical translators actually use the prototype of the system. Don't just give them words to translate. They've got to translate in context of a real system. That's often not done, and that's why translations are often, rather ludicrously funny to people in foreign countries, because they look at this and say, "What? That's a weird translation. It doesn't correspond to what the system's doing." That's because the translator didn't have the system to play with. Has anybody experienced that? Bad translations of software here? Okay, a couple of hands coming up. Right. It's notorious in Canada. I mean, there's bad translations all around the University of Ottawa, but that's not even computer systems. Computer systems tend to be worse. By the way, I have to plead guilty here. One of my first co-op jobs, when I was still in second year, I had programmed a system in English, and I was told all of a sudden that some high officials from the government were going to come and were going to see this system, and they were francophones, and it had to be translated into French by tomorrow. So here with my high school French immersion and one year of university French, they said, "Can you do it?" I said, "Well, they can't find anybody else around, so I translated the thing myself." I have no idea. Nobody ever told me how bad my translation was, but I suppose it was proof of concept, and that somebody apologized and said, "Well, at least we tried our best." That's generally speaking something not to do. Okay. User interface implementation technology changes rapidly. This is a big problem. I'm sure you've all experienced, well, maybe you're only in second year. Anybody who's spent any time programming will have experienced the rapid changes in Java and in other GUI technologies over the last few years. There's still quite a lot of change going on. But in the early years of Java, there was, we went from AWT to Swing and still quite a few changes. In the C++ years before that, changes were quite rapid, with all kinds of companies coming out with stuff. And typically new releases of software tend to change, new releases of programming languages and toolkits for UIs tend to change the UI part more than the low-level classes. Okay? Part of it is to keep up with the ever-increasing demand for cooler and better-looking user interfaces. Okay? So as Windows adapted or as other platforms adapted their operating systems, the user interfaces, toolkits adapted. And this causes problems for applications that then have to adapt to new class packages. And it can often cause a lot of headaches and a huge amount of rework to try and adapt your applications to work in newer environments. Okay, so you have to watch out for that. You have to stick to simpler UI frameworks. Don't use the latest and greatest one that's just been published, because it undoubtedly will be changed in the first year or two of its existence. You know, you can do it if you're in a large organization and you can afford to do rework if you need to. But be aware that historically there's been a tendency to have rework required on these kinds of applications. I mean, personally, I suffered quite severely from that. I had a nice system developed as part of my PhD thesis and finished in 1994, and written in the Smalltalk language. And then the vendors of Smalltalk decided that they would modernize their user interface offerings and came up with a totally new class library for user interfaces. And basically said the old one will be obsolete. You know, you have and users who buy my system had to buy Smalltalk as well. And the company refused to sell the old version. And because my system was so heavily innovative in user interface, it was doing, I had extended the library. Okay, basically what happened was that my extensions were totally obsolete, and effectively half of the application was totally obsolete because it was a UI-intensive application. Okay, it was all about browsing knowledge, and a lot of it was UI, innovative UI, totally obsolete. And even to this day, I still periodically, once a month, get a request for this application, and I say, if you can somehow obtain ancient versions of a programming language, I'll be happy to sell you a copy. Nobody buys for that reason, but anyway. But it's a problem that I've encountered through my career in companies as well, and government organizations. UI design and implementation can often take the majority of the work in an application. This may seem surprising, but the actual work to put together a good UI can be quite dominant in many types of applications. There are other types of applications where it isn't, but in many applications, they're very UI intensive because the data is relatively simple. What takes the work is designing all the forms and designing the navigation paths. Think of web applications. I mean, you know, a lot of work goes into designing the UI aspects of the web design. You might have some underlying databases in the background, but especially if you're doing informational pages, it's all UI design, right? You've got the information, you're just figuring out how to present it. Okay, and so often this is overlooked. And secondly, the fact that you have to work with users and you have to prototype and you have to do UI evaluations adds a lot of time, which is often not budgeted. And so when you're doing project planning, you have to think: is this an application that falls into this category, where UI is more dominant than many people would otherwise think? So be careful about that. And developers often underestimate weaknesses. Project managers often think, well, you know, we have trained, university-educated software developers, and they think, well, they can do a good user interface design, not realizing that they actually lack the expertise. In our software engineering program, it's compulsory. It's not compulsory in computer science or in computer engineering here, and so some medium to small fraction of those students will take it. But you'll be going out into some of you here will be going out into the workforce with this as your only background in UI design. And so you have to recognize that you have a very minimal background, if that's the case, and defer to experts, or else take courses to train yourself up to make sure that you actually do have the appropriate background. Okay? So 70, 80, 90% of people out there in the workforce don't know how to do it. And of those, a good 70, 80, 90% think they do. You know, so that's why we have a lot of bad UIs out there. Because one of the things is that, as I said, you don't realize you don't know it because you don't know what there is to realize. Okay, any wrap-up questions then about user interface issues or use case issues coming out of Chapter 7? No? Okay, well, we're going to leave the human issues behind then for now, and we're going to move back into technological issues. It's actually not quite as technological as some things. We're going to be talking about modeling interactions of behavior. Interactions can be, you can model user interactions, but you can also model system interactions, interactions between components. So we will still see a few remnants of actors showing up in the next few slides. Okay? In Chapter 5, we talked about the aspects of UML that are describing the data primarily, the classes and the methods that operate on objects of those classes. Okay? Now we're going to talk about modeling the behavior of programs, how programs change, how they send messages backwards and forwards to each other, and how they change from one state to another. And so the first part is interactions between components and between objects. Okay, basically message passing. And we're going to talk about interaction diagrams. Okay, used to model the dynamic aspects of a software system. Okay, they help you to visualize how the system runs. You don't need necessarily to create interaction diagrams of every part of your system. These are needed to model the more complex parts of the system, because the simpler parts of the system you can get away with class diagrams with methods and class hierarchies. And you can understand how algorithms are done, and you can say, okay, we'll write some pseudocode for an algorithm and so on. But when you're talking about multiple objects or multiple subsystems communicating with each other, especially when you're talking about clients and servers sending messages over channels, then you start to have to model the sequences with which these messages occur, and so on. And that's where interaction diagrams come into play. Typically what you do is you take a use case that involves a lot of interaction among components in your system architecture, and you draw a diagram that shows how these components of the system are going to interact step by step to do that. Okay, and the objective then is to show how a set of objects, okay, we're talking objects, not classes now, objects accomplish the required interactions with an actor, and the actor, of course, can be some other system. It doesn't have to be a human, as we said. Okay, so these could be the steps that are being done, could be steps of a use case, or steps of some other piece of functionality. It might be sending a message over the network and confirming that that message has been received. That's not a use case. Okay, that is communication between two parts of the system that are distributed. There's no end user or no external actor involved. So we can model use cases or other parts of the system that have to communicate. And the whole thing together is an interaction. The different kinds of messages that are being sent could be method calls. Okay, they can be considered messages. They could be messages sent over a network, the kinds of things you're doing between clients and servers over sockets or other kinds of messaging protocols. They could be various other kinds of things that are more esoteric that we won't look at in this course. Okay? So we'll think in this course of method calls and messages sent over the network. You can use these diagrams for modeling either of these kinds of things. And in the interaction diagrams, we're going to see instances of classes, actors, and then the messages. So let's actually get to a diagram. Two kinds of diagrams, sequence diagrams and collaboration diagrams. They convey a lot of the same information, but have different strengths and weaknesses, which we'll get to once we've actually seen the two styles. Okay? And one of the things that's recommended you do first is you create class diagrams, because fundamentally one of the things you're going to see on these diagrams is objects, instances of classes. So on chapter 6, on page 6, at the bottom, you're seeing a class diagram. Okay, course section, registration, course section being the association class, and students. Okay, so the registration, sorry, I correct myself there. Registration is the association class between course section and student, and then we have an abstraction occurrence between course and course section. Okay, so we have a class diagram developed, and we want to work out one of the interactions between or what happens effectively when an actor is going to interact with the system to to create a registration and add it to the schedule. So this sequence here, this sequence diagram, is showing the method calls that occur. So the actor or the user interface will send a request to register message to a course section object. Notice it's an object because it's colon underlined. Okay, which will then say create And this will create a registration object. Notice the create stereotype. Okay? And the fact that this registration object is below the baseline. You'll notice that we have course section, registration, and student from left to right. But the registration object is below, is down below. What that means is that the first arrow that hits this is the creation point. So this is created by this create message. Okay, then what happens is the registration says add to schedule to the student object and add to registration list to the course section object. Okay, so I just walk through the diagram. We'll talk about its syntax now. But I just walk through the diagram and you can see that they're relatively straightforward. They're basically visually showing the sequence with which things occur. Not complex. Very relatively straightforward kinds of diagrams to draw. And that's why we're going to go through this quite fast. When we get to state diagrams later on, we'll spend more time because they're much more deep than sequence diagrams. Sequence diagrams are important when you have interesting issues to design. It can be important to design a sequence diagram, but syntactically they're relatively simple. Let's take a look at a few of the details then. You'll notice this actor symbol I talked about. This is in some sense representing the end user, but it also can be seen as just the user interface. Okay? When we're abstracting here, we're saying somehow from the actor, from the user interface, we're getting a message coming in. We're not going to talk about the details of how that message gets into the system, but at some point it gets in from an actor to this subsystem that's dealing with course sections. Okay? As I said, oriented from left to right, we have these vertical areas. Course section, registration, student. Okay? Top to bottom is time. So time starts at the top and progresses down to the bottom. Okay? It is possible to take these diagrams and switch them so that we have objects from top to bottom and time from left to right. But typically they're shown in this orientation. It's the more common orientation. We have a sequence of arrows connecting the information associated with these objects. There are different styles of arrows. If you look in the depths of UML, we're not going to talk about the different styles of arrows that have slightly different meanings. Okay? Each of these vertical areas below course section is called a timeline. They're basically lines, dotted lines, okay, with boxes. And those boxes are called activation boxes. Basically, the activation box is saying the time under which this object exerts control. And so when the request to register message comes in, the course section object is given control. Okay? And it can keep control until the bottom of the box. And that's the activation box. It's activated, it's doing something during that time period. Before that, we just saw dotted line, meaning it's not activated. First thing it does is it sends a create message to a registration object. Now, what's going on here is we're calling. We're calling one method, calling another. So the top method still has control. It's calling a secondary method, which then has a sort of sub-level of control. So it has an activation box too. The top method is being blocked. Okay, once the course section sends a create message to the registration, effectively calling the constructor, okay, the course section, this activation box continues because it is now not doing, it's active in the process of waiting for the return to come back. You can't do anything else with it. Okay? Now, this is called synchronous control. There's another thing called asynchronous control where once you send a message, you can get on with other stuff. We're not going to talk about that, but that is another style. And you see different looking activation boxes where once you send a message, the activation box ends, and then you can do other things when you receive another message. That's asynchronous. But here we're talking strictly synchronous. Okay, so the registration constructor is underway in the middle, and its activation box starts at the beginning of the timeline and ends once the constructor finishes. And one of the things it does is it calls add to schedule to the student, which starts another activation box to do that piece of computation, and returns. And then it calls add to registration list to the course section. So it's calling back to its caller, in fact. and is calling another method in its caller. You can actually diagram this. The activation box can sort of look like this, so that to show that, in fact, we have a secondary piece of work going on. Another thing that you can do is you can show the returns as dotted lines. So what I could do is I could say I get a call and I get a return here. I can do that. You can leave them out, or you can show them depending on whether you want to clutter up your diagram or whether it makes it more clear to show the return points. Okay, so that's a simple example of a sequence diagram. Any questions about it? Okay, now I'm expecting you to be able, coming out of this course, to be able to basically take a sequence, to take a method, for example, or set of methods in a class, and be able to translate it into a sequence diagram. You should be able to understand the sequence with which things can occur. After all, it's just step 1, step 2, step 3, step 4, and you should be able to translate that into a diagram like this. Not much more complex than this. Okay, that's the skill. At the University of Ottawa, the next course, SEG 2101, will spend a lot of time on this kind of area. Okay, that's a big topic, is timing and sequences and a bunch of other pieces of notation for designing scenarios and issues like this. Okay, slide 7 is talking textually about the various things I just talked about orally, so I'm not going to go into slide 7. Okay, it's just talking about the same things. Slide 8 shows a slightly more complex sequence diagram. In this diagram, I've just added a few more things. You'll notice that I am showing the dashed lines for the returns, so you can do that. I am showing the arguments that can be passed. So request to register, bracket, a student. Okay, I'm showing the argument. And in fact, over here on the third object is that object, a student. So it's being passed, in fact, from the graphical user interface to the course section. I'm separating the actor from the graphical user interface, just to show that you can do that if you wanted to. The graphical user interface is part of the system as an activation box saying it's active, but the end user, can do other things, right? The end user is not sitting necessarily waiting for this. Theoretically, their brain is doing other things, so I'm just not showing an activation box there, just to illustrate the point. Hopefully, of course, this would return in a fraction of a second, so the user wouldn't have time to do anything else. But conceptually, they aren't locked, neurologically locked to the computer, waiting for the return to come back. Okay. We see an assignment. Has prerequisite gets assigned to has passed course with an argument. Okay, so we can see that the return value of a certain call can be assigned to a variable. So when I send this message from course section to the student, the result is returned in this has prerequisite variable that I can then use. Down below we see brackets, square brackets, condition, has prerequisite. That means only do this if. Okay, so UML's notation for a condition looks like this. Has prerequisite. Okay, this has got to be some expression that evaluates to true. Okay, it's like OCL, except that here you can use a programming language style if you want. This style here is a typical style you would use in UML, and it looks pretty similar to Java in some respects. But the brackets is the condition. You don't say if this then that. You just put it in brackets and you say this is the if. Only send this message under this circumstance. So what we're saying is we're only going to create the registration for the student if the student has the prerequisites. The previous call was saying find out if we have the prerequisites. Have they passed the prerequisite courses? Okay. The one before that was saying get the prerequisites. Okay, so at the top it says prereq colon equals get prerequisite. Okay, notice a colon equals is the assignment. Okay, it's not equals, it's not actual Java, it's UML. So we're getting the prerequisites, we're then finding out if we have the prerequisites, And if we have, we're creating the registration and adding it and so on. Okay? So the main pieces of notation to pay attention to here are the assignment to a result of a message and the condition. Any questions about that?
Suppose now when we are evaluating the has prerequisite, suppose he doesn't have the prerequisite.
Then we just don't do this and we keep on moving on down and we do whatever comes next, which turns out to be nothing.
So we don't need to, like, for now, if you're doing error handling, so don't we need to show that we're doing that? Or?
Well, you could have the next line could be does not have prerequisite. Okay, so not has prerequisite, and then it would be one or the other. That's the else case. Okay, effectively, and so you wouldn't, you would go on down till you found a condition that is in actual fact true and do that. So there are ways of showing the else case. But you'd show them as conditions and only send this message and do all the other stuff associated with that message under these circumstances. Okay? You might wonder why we don't use actual Java notation here, why we use colon equals instead of equals. And the reason why UML has its own notation is to try and be programming language independent. Okay, so this can be used for any programming language. It's supposed to be independent. In fact, some of these things might be things that are not actually implemented in programming languages. You can, as I said, you can use these to show protocols between various distributed clients and servers, and there might be a whole bunch of code associated with choosing which messages get sent. That it's not just simple assignments and things like that. Might be much more sophisticated mechanism involved. So here we're just showing what actually gets implemented as code within one set of objects talking to each other inside a running application. But we can also show sequence diagrams for distributed systems. Any more questions? Okay. Okay, we'll add a little bit more notation then. Slide 9. We now have a bill object. We have a set of purchase objects. Notice that there's the notation for a collection of things in UML. I showed that to you the other day, where you have overlapping boxes. What you're saying is treat a bunch of things as behaving the same. Okay, so a bunch of purchases and an item object. Okay, so the first thing the bill is going to do is it's going to, so the star followed by something in square brackets is effectively the looping operation. So star means operate on all of these things. For all purchases, get subtotal. Okay? And so we're going to send this message to all of these things, the get subtotal message, get subtotal message, get subtotal message, for however many of these purchases we've got. Okay? Each of the purchases, once it's activated, will get the unit price from the corresponding item. Okay. And then once all of that is done, once you've looped over all of the purchases, then we're going to compute total. And notice this piece of notation is sending a message to ourselves. So it's calling a method within our own object. Okay, it's a reflexive call. We're not calling a method in some other object, we're calling another method in our own object. Okay, so these are just two more pieces of notation, or three more pieces of notation that I wanted you to be familiar with. The fact that we can show multiple, these are called multi-objects. Okay, the difference between a class and a multi-object. A class represents a set of objects for sure, but you're then talking about a unit of programming, a unit of modularity. A multi-object is a representation of a collection of instances which are going to be all treated the same. Okay, so we're in the instance domain here. We're not talking in the classes at all. We're talking strictly instances here. It just happens to be that several of them work the same way. So rather than showing showing them separately horizontally and repeating the same get subtotal over and over again, especially as we don't know how many there are. We show 3 here, but that just means some number, which we're not specifying. We don't know how many there are, but there is some number of these. In the class diagram, we see purchase as a class, and Bill has many purchases. And so the class diagram, we just show the star. Here we're showing a multi-object because sequence diagrams work on instances always. They don't work on classes. You don't show classes in the sequence diagram, you show instances. Okay, so any questions about the multi-object, the asterisk condition, meaning things to do with or selecting. Inside the square brackets, I could have some phrase that would select a subset. So I could say for all purchases greater than $1,000, which would mean I'm not going to send this to all purchases. I'm only going to send it to the ones greater than $1,000. Okay, that's why we have a condition in square brackets there, because it allows me to limit and control which subset. But in this case, I am using all. Okay. Again, we've added a little bit to the syntax, but this is, we're almost there. There's only one more bit of syntax. In fact, we'll go to that now. Okay. So on slide 10, I'm showing object destruction. So let's walk through this scenario, or this sequence. The actor, the user interface, cancels the booking, calls cancel booking on the specific flight object, which in turn calls cancel on the booking object, which in turn calls delete from itinerary on a passenger roll object, and delete from passenger list on specific flight, and then dies. The object vanishes out of memory. That's what the X means, the big black X. It means this is the end of the existence of this object. So effectively, this is the. It should be the case in a garbage collected environment like Smalltalk, Smalltalk too, but like Java, that there's no other reference to the object, so the garbage collector can collect it. If you were implementing this in C++, there would be a destructor call at this point. You'd have to call the destructor to get rid of it. Questions? Okay. Okay, so that's a quick look through sequence diagrams. As I said, sequence diagrams are notations where you lay out on two dimensions. One dimension is the object, the other dimension is the time. And they tend to take quite a lot of space to do this. And therefore you don't show every single piece of code this way, because if you had, let's say 10,000 lines of code in your system, you'd end up with probably getting on for 10,000 pages of sequence diagrams. You do this when you have particularly complex bits of your system that you want to explain more carefully. Collaboration diagrams are a more compact way of showing interactions. In collaboration diagrams, you have the same objects. Okay? So here we're seeing course section, registration, student. The same objects as we saw a while back in I guess it was slide, course section, registration, student. Where's my registration? Yeah, slide 8, we had that. Course section, registration, student. Slide 6 was the canonical. Okay, so slide 6 is a sequence diagram. Okay, where we're seeing the sequence with the time dimension going down vertically. And then on slide 11, we're seeing the same information. But now we're not showing the time dimension. We're just showing on a bunch of lines connecting the objects the messages that will flow over those connections. Now, if you're following the law of Demeter that we talked about, this rule of only sending messages to your neighbors, what's going on is that you're sending messages over the links between classes that are effectively modeled as associations in the class diagram. Okay, so these lines are links in the instance diagram. But if you're not following that law, you may end up with situations where you have to have extra links that are purely for the purpose of communication. Okay, but ideally, your communication links are also your object connection links, as much as possible. And so here what we're showing is that number 1 we call create. If you look back at the sequence diagram, you'll see that was the first thing we did. Number 2, we add to schedule. Number 3, we add to registration list. And we see these little arrows saying the direction of this communication is occurring. and that we have to put numbers. We have to have a numbering sequence 1, 2, 3 so that people can tell which order things happen in, because previously we could just look vertically and see the time dimension. Now the time dimension is shown as numbered steps. Okay? And so the set of things that are occurring and the link between two objects, in this case create and add to registration list, represent the collaborations that these objects do with each other. Collaborations represent things happening, objects working together to do things. We saw this term expressed earlier on in the end of chapter 5, okay, when I talked about the collaborating objects that get together to implement an association. Well, that's exactly what's going on here. Okay, these objects are collaborating in order to work together to create a registration. And so that's why these are called collaboration diagrams. Any questions about this syntax? Okay, so they emphasize how objects collaborate to realize an interaction as opposed to all the time dimension. Sequence diagrams show the time dimension heavily, whereas when you glance at a collaboration diagram, you're seeing objects and lines between them. That's what dominates your visual field. And so you're seeing the collaborations. And the actual messages are sort of attached to these lines. Okay, the objects are vertices and the lines are the collaborations then. Slide 13 shows another slightly more sophisticated diagram. This is the one I think that corresponds to slide number 8, where we now have the student in the course. Okay? So, again, step 1, request to register, bracket a student. Same thing as we saw before. We can have all these variables. We can have these return values. Step 2, prereq, colon equals get prerequisite. So we're assigning the value of this return, and it's being returned back. The prerequisite is being returned back to the course section once we return from this message send. Step 3, has prerequisite is assigned to a call to get to has passed course. Step 4, if we have the prerequisite, and only if, condition, same syntax. Then create. Step 5, call add to registration list, back along the same collaboration line. And I guess this should be 6, add to schedule. They're definitely not supposed to be both 5. I hope the book doesn't say 5, 5. If it does, that's a bug I got to get fixed for the next printing. Okay, so same information pretty much as in a sequence diagram. But you notice the difference, right? What's the difference? What information am I showing here that we haven't seen before? Sorry? Yeah, it says the thing that says parameter, it says local. Okay? So these are UML stereotypes that basically say where's the information coming from. Okay? So for example, when we say parameter, okay, what we're saying is that the student, okay, was originally a parameter of the course section has obtained this student as a parameter. Okay, the GUI has obtained the course section as a local variable of some method that ends up calling it. It's got a handle on the course section as a local variable. It's not an instance variable. It could be an instance variable too. You sometimes see that. The registration has obtained the course section as a parameter of the call, and so it's also obtained the student as a parameter. Okay, so it's just saying where did the caller get the information from when it was going to send a message. Okay, and there's a number of these things. If you look in the book, there's a few more listed. If you look in the UML specifications, you see a few more. So it's just showing you a little bit more information you can add to the diagram if you want. Any questions? Okay. And in fact, the next slide, slide 14, is talking exactly about these things. Okay? We're saying that there are a number of reasons why, one is being a local variable, one is being a parameter by which you've got access to the object you're sending a message to. And so, at the bottom of slide 14, the classes can have an association between them. Okay? And so typically if they have an association, you just don't label it. And so, for example, going back to slide 13 for a second, interaction 2, okay, message 2, it says colon equals get prerequisite. It doesn't say angle bracket, association, close angle bracket, because that's the default. Okay, something is if there's an association, as there are between course section and course, we don't have to say that explicitly. Okay, that's already been set up. That's the normal case. Jumping forward to slide 15, could be a local variable. Okay, that's clear enough. Okay, so if an object has a local variable in its hands, it can then send a message to that local variable. So and if it's got a parameter, it can send a message to that was passed to it when something was invoked on it. It can then send a message to that parameter. Okay. So there's a little bit more information about the links that we see, the communication links we see on these collaboration diagrams. Questions? Okay. Global and network are two others. We haven't seen them here, but if you use global variables, you can send a message to a global variable. If you are communicating over a network, to an object that's somewhere else on the network, you can tag the thing as network. Okay. So these are just examples of things that you can do to say where the object, how to send a message to an object. How do we get hold of this object? Okay. So how do we choose between a sequence diagram and a collaboration diagram? Well, you use a sequence diagram if you are concerned about making the time dimension very visible. And you want people to clearly see how things evolve over time. So we show time in this vertical direction moving down. Okay? And that can be important if you've got very complex things happening at different points in time and you want to make that explicit. Okay? Sequence diagrams also have more space. Because they take up more screen real estate or more space on the page, they have more space for details of messages. You can imagine that if you're sending messages backwards and forwards, okay, between the same two objects over time, okay, so you've got some message descriptions here and here and here. Okay, on a sequence diagram, you've got space to do that. On a collaboration diagram, I've got one line between the two things, so I'm going to have to say one, do this, 2, do that, 3, do that, 4, do that. And it becomes hard to read. Okay, so if you've got lots of things going backwards and forwards, you've got more space on a sequence diagram. You can make it vertically continue page after page after page. Collaboration diagram becomes messy after you've only got a few messages sent between two objects. Collaboration diagrams, because they contain, in some sense, collaboration diagrams contain one object per class in a class diagram, typically, if you think about it. And that can be considered mathematically as a projection of the class diagram from class space to instance space. We have one canonical instance representing each class in the class diagram. And we're showing all the messages that can be sent between these instances. Of course, we might end up with situations where we have to show two separate instances because they have different behavior. But it's sort of a projection. And it can be used to help you quickly work out what the sequences might be. I'm just going to get an eraser for a second here. So for example, if I say to myself, well, I have okay, A, B, and C, okay, and these are going to be this is my class diagram. I have an association here, I have an association there, let's say. Okay. Now I want to work out a sequence diagram from this. I might informally just write some, I might say, okay, imagine these are instances, okay, for a second. Just keep everything the same, take out my multiplicity perhaps. And I might say, okay, well, message 1 is going to be from here to here, and here's the name of it. Message 2 is going to be from here to here. Message 3 is going to be from here to here. So I can sort of work with my class diagram, work out some messages, brainstorming. I can be playing around with it, erase them. You know, I'll say, okay, well, actually, we have to do this. This is the third one. You know, and draw on the class diagram until I got it worked out, and then start fleshing it out as a sequence diagram to add more details. Okay? So it can be used as a sort of stepping stone to get to a sequence diagram. A number of things you can do informally like that. Another interesting issue relating to collaboration diagrams is their relationship to patterns. So on slide 19, I'm showing at the top the proxy pattern shown as instances interacting. So I've got a client object, a proxy object, and a heavyweight object. And I'm showing that the client sends a request to the proxy, and then in message 2 it says condition, information needed and not loaded. If the information is needed but not loaded, then load heavyweight. So I'm showing the interaction involved when I make a request to a proxy where we have to actually load the full image into memory. Okay? There's a funny little squiggly box on the version I'm showing here that I think only shows up in some platforms. That's not supposed to be there after loaded. Okay? So here we have a collaboration diagram. At the bottom, what I'm showing is a piece of UML that shows how a pattern can be expressed in even more abstract way. These ellipses with dashed lines, a dashed line ellipse with dashed lines pointing to various parts of various classes, is how you represent the same information or similar information about a pattern. Okay, this proxy is a named collaboration that involves a student in a proxy role, a client a course section in a client role, and a persistent student in a heavyweight role. So notice this is actually a class diagram at the bottom. These are actual classes now, but I'm showing the roles with which these things play in this particular collaboration. So different ways of expressing. If you go back to the proxy, you'll see another way of expressing it. Go back to the pattern in chapter 6, you'll see how I showed it as a class diagram. Here I'm showing it as a collaboration diagram and as another form of class diagram where we actually use the term collaboration for this ellipse. Okay? So I've spent this class so far going through interaction diagrams, which are one of the two main kinds of diagrams involved in expressing the behavior and evolution over time of a program, okay? The message sending issues. There are two kinds of diagrams: sequence diagrams, collaboration diagrams. Interaction diagrams taken as a whole are relatively straightforward. I expect you to be able to draw very simple ones because the concepts behind them are easy. Okay? Next class, we're going to move on into state diagrams. State diagrams are deeper, and we're going to be looking into them in quite a bit of depth. Okay? So we're going to stop today, and we'll move into state diagrams on next class.